Hey everybody, so we're back. Now, so far this unit, we have taken a look at how tension, friction, the normal force, and even gravity can cause an object to go in a circle. What we haven't talked about though, is what happens if this perfectly uniform circle that we've been talking about so far, a horizontal circle with a constant speed, meaning the magnitude of the velocity is the same all the time, is suddenly turned vertically. What happens to the forces once gravity becomes a little more involved? And I think the answer is obvious once you've seen it. But until you've seen it, it gets a little tricky. So I think the easiest thing that I can do is to do a quick demonstration utilizing a bowling ball. Now, if you have a bowling ball at home, you should tie a string around it and start swinging it around. Because once you do, you can't forget how the forces change when you're spinning a circle in a vertical plane. Let's get to it. So I do this demonstration every year. And every year, the next day, my back hurts. Why do I still do it? I think I'm slow. But here's the thing. With a large bowling ball, even though you are not the person swinging it, you can still physically feel it as I swing this ball. That is, after all, why we watch sports, isn't it? It's not to see who wins or loses. It's to actually put yourself in the position of the person that's out there on the field or the court or what have you. As human beings, we have the ability to put ourselves in another's shoe, and we don't even realize we're doing it most of the time. Let's utilize that when we take a look at this ball going in a vertical circle. So here I got a bowling ball. It's heavy, obviously, and I'm getting weak. But here I've got it hanging by a string, and there's clearly tension in the string. There's mg down, tension up, and the sum of those forces is 0. Good. So at that moment, the tension and the weight, mg, are equal. But if I get this ball spinning in a vertical plane, we can see that the tension changes. Now, I don't know if you can see how hard I'm working here, but at the top of the swing, it's not that hard at all to make it go in a circle. But at the bottom of the swing, it's pretty heavy. Now, would it count as workman's comp if I took my own legs out with a bowling ball? I don't know, but I'm pretty sure I'm going to find out by the end of my career. What did you see there? Did you see how it was obvious that the force I had to apply with the string changed as the ball was going around in its path? Let me put this down. Let's take a look at a diagram. Just like any other physics problem, they can get a lot more complicated. So what we are going to do when we look at vertical circles is, for the moment, we're going to focus on just what's happening at the top of the circle and the bottom of the circle. Maybe later on in the year, we'll get back to what's going on at different points on its path. Let's take a look, like we always do, at what are the forces that are acting on the mass at both the top and the bottom. Now, when I look at the top, what I see right away is that gravity is acting down, mg. What other force is also acting down on the mass at that point? Yes, of course, tension. I'm going to draw that tension a little bit smaller. Because at the top, what I have, if I were to redraw those two vectors, tip to tail, would be I would have mg down and tension down, adding together. Now, let's take a look at what happens at the bottom of the swing. At the bottom of the swing, I'm still going to have mg down, and that quantity doesn't change. It's still just the weight of the ball. But acting up is that tension, and that tension has to be much greater now. In fact, if I were to draw in the free body diagram at the bottom, I would have mg down same length as before, and my tension would be much greater. If I added those tip to tail, watch. If I added those tip to tail, I would have mg. And you know what I would end up with? A resultant that is the same order in magnitude, just in the opposite direction. Wow, this is how physics teachers can make things harder than necessary, just like that. Because here's the thing. The tension changes. Clearly at the top of the swing, it barely took any tension in order to get that object to continue to travel in a circle. Why? Because it was getting help from gravity. At the bottom of the swing, however, it took a lot of tension in order to keep that going in a circle because gravity was acting against it. And just like every other system we have looked at this year, we can say the sum of the forces will cause the mass to accelerate. In this case, the sum of the forces is going to cause the mass to go in a circle. And lastly, when I sum up the forces, what direction do you think is going to be the positive direction? Yeah, that's right. In the direction of the centripetal acceleration. So toward the center is the positive direction. Good. Write that down. Hopefully you can zoom in here and it'll look good. I'll get my crew on it. Towards the center is the positive direction. All right. How about we look at some math? All right, so let's sum up those forces. Let's take an example. Well, let's take the example of what's going on when it's at the top. Okay? At the top, we are going to have mg down as well as tension. So if I say the sum of the forces causes the mass to go in a circle, I can say plus tension plus mg causes the mass to go in a circle. Now, what I like about this is we're starting to get to the sense of when I solve this, these aren't just letters, it has meaning. When I get tension all alone, it's going to be mv squared over r minus mg. Essentially, the tension necessary for it to travel in a circle is going to get help from mg, so the tension is going to be less. Now, when we're at the bottom of a swing, we're going to have mg down. If the speed, let's say 5 meters per second, was the same at both the top and the bottom, then the tension has got to be much greater. So the sum of the forces is going to cause the mass to go in a circle, but this time, when I sum up the forces, it's going to be plus tension minus mg causes the mass to go in a circle. So now when I solve it up for tension, I get mv squared over r plus mg. Here's the thing. Now tension is not only causing it to go in a circle, but it's also supporting the weight. And that's what's different. So, all right, we're back. And you know what? After that brief break, I decided instead of swinging a larger ball, I'm going to go with a smaller one. Okay? And as I spin that around, the tension is clearly changing as it goes. Now, I also see the velocity is changing slightly. But for the moment, we're going to let the speed stay constant. So in this problem, I'm going to say that I have a bowling ball. Write this down. Here we go. Let's say that the mass of that ball is going to be equal to 1.5 kilograms. Let's say that the speed, I was able to keep it constant at 5 meters per second. And the radius
When I did this earlier, I measured it out, and I got 1.2 meters long. So the question is, what is the tension at the top and bottom of the swing? Go ahead, write that down. Nice. I know that some of you right this moment are not writing that down because you're already doing the math. You just can't help yourselves, can you? All right. Here. At the top, I just derived a formula that said tension equals mv squared over r minus mg. Okay. Now, the mass, 1.5. Could I factor that out? Yeah, I could. Not at this moment, though. Velocity of 5 squared divided by the radius minus that 1.5 times 9.8. And the tension in the string good. I know you guys already have your calculators out. You're such good students. Well, some of you. I'm just kidding. You're all great students. You're all above that. I'll stop there. I got 16.6-ish newtons. Okay? Let's take a look at the bottom. See how much that tension changed. Now, in this problem, the bowling ball doesn't quite have the same mass. So it might not be as dramatic as when I was swinging the big one around there. But the tension, as we derived earlier, is going to be equal to mv squared over r plus mg. So let me take those numbers and plug them in. Can you see that it still takes the same amount of force to make it go in a circle? The same net force, but this time tension is providing that net, the sum of the forces, plus the gravity. Go back to my calculator, hit second function entry and change the sign. And I got about 46.0 newtons. So it's pretty substantial. The tension varies in a vertical circle. But those aren't all of the problems we can do. There's other problems as well. One of them, which I thought was just about to come up as I was swinging that, is what is the minimum velocity necessary to, quote, make it over the top?